So in today's lecture, we take one more example on Ponchon-Saverett method, and here also we will address, the reboiler load, condenser load, how many plates are required, and in addition to that, we will see how we can calculate the number of plates at infinite reflux ratios, and how do we calculate minimum reflux ratios. All right. So this is the second example on Ponchon-Saverett method on the distillation column based on your enthalpy energy balance. All right. So let's see how do we address this problem here. So this is example 2. In continuation of this, our discussion on Ponchon-Saverett method. All right. So now we are looking at methanol water solution. Okay. So what is given here is we have this methanol water system feed. It's brought to the distillation column at certain rate 5000 kg per hour. All right. And the problem statement says this feed is 50% weight methanol. So weight fraction is given 50%. And then we have the top product is purified to 95% methanol, and the bottom product is 1% methanol. The distillation pressure P is 1 atmosphere and temperature is 26 degree centigrade. All right. So problem also says that there is a total condensation and we have the reflux going back to the distillation column, or the feed is preheated, etc. But what we do right now, based on the information, the first few sentences, that feed is so much, flow rate, so much is the compositions, this is the XD, this would be your XW. Let's see what we can do or we can calculate before we proceed further. All right. So the question at the end of this lecture, we should be able to answer how many plates, how do we calculate number of plates, how many plates we have at infinite reflux ratios. All right. What is the minimum reflux ratio, and what would be the condenser load and boiler load. All right. So before we go through the problem here, let's see what we can calculate based on whatever information we have given to us. So the first thing we must realize that this is 5000 kg per hour. It's given in the weight flow rate, mass flow rate. We must convert into mole fractions, molar flow rates. So which means F will now be 5000 into 0.5 divided by the molecular weight of methanol, 32, plus 5000 multiplied by 0.5, and we have 18 molecular weight of water. So this is a methanol water system. All we are trying to say before we proceed further, in solving this, in applying this Ponchon-Saverett method to answer these questions, let's see. Now we can write in the form we need in a mole fraction basis. So everything is a weight fraction basis. We are converting into this mole fraction basis. So this is 216. We calculate 0.8 kilomole per hour. Okay. So again, the weight fraction is given as 50%. We will like to convert this into mole fractions. So ZF, now again we are using this nomenclature for the feed composition because we do not know what is the status of this feed here, if it's a liquid or it's a vapor. All right. So we are using this nomenclature ZF, and ZF would be in mole fractions, would be 5000 multiplied by 0.5 divided by 32. So this is the moles, total moles of methanol over the total moles which we have got, which we calculated from here, 216.8 to make it 0.36 mole fraction of methanol. All right. Similarly, XT is 95%. Then in mole fractions, we can convert this into 95 over 32 divided by 95 over 32 plus 5 over 18 to make it 0.92 mole fractions. Similarly, XW mole fractions, we have been given 1%. So 1 over 32 over 1 over 32 plus 99 over 18 equals 0.0057 mole fractions of methanol. All this is methanol, more volatile component or large more volatile components. Okay. So we have not yet completed the statements, the problem statement completely here. So it says 5000 kg per hour of methanol plus water system is brought into the system. Top product is 95% weight basis. The bottom product is 1%. That's also weight basis. All we have done, we have applied our previous knowledge of stoichiometry to convert all the quantities into mole fractions. So that's the first thing you should do as a good habit, because very often, all enthalpy data or the TXY diagram, everything is given in terms of mole fractions. So everything should be converted into kilomoles per hour instead of kg per hour. Weight by weight, instead of weight by weight, you should have moles per moles here. Okay, so let's continue with this problem here. Now again we have this column. Okay, feed F, top product here is D, bottom product is W. So without again going into the problem statement and what are the other quantities, let's see if we can calculate D and W. So we write F as 216.8 equals D plus W. Again we can write a species balance for methanol F into ZF as D XD plus W XW. Alright, so here F is given, D is given, D and W we are supposed to calculate, ZF is given, XD and XW, all these quantities we have calculated, two unknowns, two equations to obtain the molar flow rates for the top species. Top product is 84.4 kilomole per hour. Alright, similarly W, bottom product residue is 132.4 kilomole per hour. So I leave this as an exercise, a very simple calculation to calculate D and W. Now again, very often you will see that we also need to know at some point of time the average molecular weight of feed, average molecular weight of the top product, and the average molecular weight of this bottom product, because you have to do a lot of enthalpy calculations here. So before we further go, let's see if we can get molecular weight of average molecular weight of the three streams here. Okay, so if you do this, say for example MD, average molecular weight of top product, then we have 0.92 into 32 plus 0.08 into 18, so this would be your 30.88. Alright, similarly if you have molecular weight of MW, which just now you calculated, so this 0.92 is nothing but your XD, which you have calculated, mole fraction, so multiplied by the molecular weight, then you have water 0.08 multiplied by 18, so this would be your kg per kg mole. So we are calculating MD, average molecular weight of your bottom product MW, this would be 0.9953 into 18 plus 0.0057, just now we calculated, to 32 to make it 18.1 kg per kilomole. Alright, similarly we can calculate, should be able to show that average molecular weight of the feed is MF is 23.1 unit. Alright, so far we have done very simple calculations for distillation column. Okay, the feed three streams, one feed F, D and W. Okay, now the problem here says that the feed which is brought into this column is preheated. So what we have here is feed is preheated. Alright, so we have heat exchanger here by which this feed is heated. before we send this to distillation column. So feed is actually at 26 degrees centigrade, and we know the flow rate of feed, we know the composition of this feed except mole fractions and molar flow rates, temperature. This is heated. Now how do we heat? The problem says that the the residue, the bottom product W, is used to heat this feed here. So we have some kind of heat exchanger here in which feed is heated from 26 degrees centigrade before it's sent to this distillation column, and this W, which is the molar flow rates of distillate residue here, it's brought to this heat exchanger and then we heat to this. Now going back to the discussion, in the earlier lecture we said that we need to do a lot of enthalpy balance or enthalpy calculations. So if you recall, in our first few lectures we said that how to calculate enthalpy given the feed compositions or given the composition of the stream and the temperatures. In other words, one has to go back and see this Txy diagram and Hxy diagram. How did we obtain from the knowledge of sensible heat capacity and latent heat of evaporations and the heat of the solutions. So in this problem it says that the feed temperature about 26 degrees centigrade. Now it's heated with this bottom product residue. Now you recall in our previous discussion that we have this reboiler in which part of this liquid which trickles from this bottom plate is sent back to the distillation column. That means the boiler acts as a theoretical plate, and the stream leaving the bottom this boiler is saturated, or it means the vapor going back to the distillation column and the bottom product, they are in equilibrium. So if we know the feed compositions and we know the temperature, one can calculate this enthalpy. All right, so one has to go back and recall this Hxy diagram. So in all these cases Hxy diagrams are typically known, right, or one has to construct it from the knowledge of a specific heat or heat of solutions, the discussion which we had in the first few lectures. The more important here to realize that this bottom product comes out of a boiler. All right, so this is the boiler in which the bottom product W goes out of this, and part of this vapor goes into back to the distillation column. So we had the last plate NP, so this would be LNP. So this is the bottom product from the bottom plate. It comes to this boiler. Part of this is vaporized as GNP plus 1. Now more important here to note that this two streams, the residue W and the vapor which goes back to the distillation column, they are saturated. That means if we know these compositions, W in this case, which we know here, this is given as 0.0057. All right, if we know this, that means we can find out the enthalpy of this bottom product HW. So knowing this feed compositions, knowing this composition alone for this stream and saying that this guy is saturated, right, in these conditions, we know this enthalpy of this stream here, HW. Similarly, if you look at Txy diagram, this one also you have equilibrium curve Txy diagram. Then if you mark X here, if you know 0.0057 here, then we know this temperature of the stream feed W which goes to this heat exchangers. In other words, we are saying here that knowledge of Hxy diagram and Txy diagram, from these two we can calculate the enthalpy of this stream and the temperature of this stream. All right, because we are qualifying by saying that the two streams are in equilibrium. All right, so or it's saturated. So we have this saturated bottom product. This feed and this product can also be cooled further or it can also be heated. In this case, it's saturated. Once we make this a statement that this stream is saturated at this and the composition is so much, XW is 0.0057, we can come to this Hxy diagram. We can calculate the enthalpy HW. So we can read from the graph, as well as we can know the temperature of this stream here TW, and this stream goes to this heat exchanger to preheat this feed here. In other words, now let's come back to this heat exchanger here, because we have to find out the temperature of this feed which goes to this distillation column. All right. So here we have W. We calculated the flow rate of this W, which was 132.4 kilomole per hour. All right. Since we know the molecular weight, we calculated the molecular weight of this bottom product 132.4. Multiplying this by this molecular weight, one can also calculate the total kg or mass flow rate, 2396 kg per hour. All right. Now F is given to us as your problem statement. We have 216.8 kilomole per hour, which corresponded to 5000 kg per hour. So we require sometimes this data as well, 5000 kg per hour, because it depends upon the values how we obtain from this literature, whether it's a per kg or per kilomole. So here this temperature was given to us as the speed was 26 degrees centigrade. This is your TF here, which we want to obtain. The problem says that this residue, it leaves this heat exchanger at 37.8 degrees centigrade. Now this temperature is also known from HXY diagram. All right. If we go back to this HXY diagram or TXY diagram, if you go back to this TXY diagram for methanol water system, then for 0.0057, which is the composition of this stream, saturated stream, this number will turn out to be 99 degrees centigrade. All right. So all we have to do is to make a heat balance here. 5000 kg per hour multiplied by Cp, specific heat, which if you read the literature, this is 3852 joule per kg per Kelvin, multiplied by Tf minus 26 degrees centigrade. So this feed is preheated from 26 degrees centigrade to Tf by this W residue, which is as 2396 kg per hour, 2396 kg per hour, multiplied by specific heat of this product, which is from the literature 4179 joule per kg per Kelvin, multiplied by the temperature difference. This feed was 99 degrees centigrade because it is saturated. So we read from here, from this TXY diagram, what corresponding to this 0.0057 mole fraction, which is XW. So 99 minus 37.8. So now we have feed temperature TF, or capital TF, as 57.8 degrees centigrade. All right. So now we know the feed which enters the column has the flow rate 216.8 kilomole per hour. It has compositions ZF as 0.36. Its temperature is, just now we calculated, 57.8 degree centigrade. All right. Now what is the status of this feed? Again, one has to go back to this TXY diagram. Now if you go back to the same TXY diagram for methanol water system, all right, and we take this number 0.36 for the feed, one should be able to read this number as 76 degrees centigrade. That means the feed is saturated at this temperature 76, and what feed enters this distillation column is colder, 57.8 degrees centigrade. All right. So all we are trying to say here that we require all these informations, TXY diagram and HXY diagram, to know the status of the feed or the different streams which we leave. All right. So now we come back to this. Now we start this HXY diagram. Okay. So we have this HXY diagram, and we will like to mark as many as points possible there. So HXY, and we have this HV, and we have this HL. HV, and HL. Alright, now feed is here 0.36. Alright, and we said that this feed is cold, that means this temperature, this enthalpy of this feed, if you calculate, this will fall short from here. So if this is the saturated conditions, if the feed is saturated, right, then the current feed is at, say, numbers is 2530 kilojoule per kilomole. So again, this HXY diagram has to be read or interpreted in conjunction with this TXY diagram. So our feed composition was 0.36. We realized that this temperature is smaller than the saturation temperature. All right. Now top product we have calculated XT as 0.92. This is 0. This is 1. Now the problem says that we have total condenser and the reflux is saturated liquid. That means if you recall the composition of the vapor which leaves the top plate and the enthalpy is G1, we have total condensation. So this is QC and this top product is saturated. That means HD corresponding to this XD, all this can be located at this HXY diagram because this is saturated reflux. One can also in principle can further cool this liquid which goes as a product, part of it goes as a reflux to the distillation column, but in this case it says it's a saturated reflux, which means if we know XT in this case, which we have calculated 0.92, this should give us HD, which we can mark as 3640. So all we are trying to do is mark the coordinates as much as we can do this. For example, for this feed we need this composition 0.36. We realize that it's cold. One can calculate the enthalpy to reach 2500. So this is the status of your feed here. Top product is 0.92 mole fractions, saturated liquid, so we know this HT here. All right, and then if you recall that the sky would be, this coordinate would be HG1 here because we have this latent heat of vapor. So whatever vapor comes from the top plate, it's condensed completely to this liquid form. So this HG1 we can mark here, the enthalpy of this stream leaving the top product or entering this condenser here, and this number is 38,610. So we can mark this point, we can mark this point here. We have also marked this point here. Okay, and now the first the question is that if the reflux ratio is 1.5 times R min. Okay, so that means one has to calculate this minimum reflux ratios. If you recall from our previous discussions, we had the extension of this line and somewhere we had this del D or we had this Q hypothetical stream leaving with this energy of this Q dash here. But in this case we do not know the reflux ratio. Reflux ratio is 1.5 times R min. If we know the reflux ratios, then we can mark this segment based on this difference between HG1 and HD. Alright, this HD is same as HL0 because the enthalpy here is same as HD. Okay, so in this case first thing is that we have to calculate this minimum reflux ratios R min. Okay, so let's summarize this problem here. If you read the problem statement, now it will say that we have certain quality of feed. So flow rate was given and the composition was given, the temperature was given, and all these quantities we were given in this weight fractions. Top product, bottom product, everything was given the weight fraction. So first thing we did, we converted all those quantities into mole fractions. This is what you should also do, convert all the quantities into mole fractions, because very often we have all the enthalpy data and thermodynamic data in terms of your mole fractions, HXY diagram, etc. Okay, so we converted all those, we made overall material balance, species balance to calculate F, D, W, XF, XT and XW. Then the problem says that this feed is preheated with the residue before it enters the distillation column. So we know the feed composition, we know the feed temperature. Now we know the composition of this bottom product. On top of that, it says that the bottom product is coming from your reboiler, which is saturated. All right. So if it's saturated, we know the composition. We can go back to HXY diagram. That means we know its temperature. We can find the enthalpy. One can make an energy balance, which we did, to calculate the temperature of this feed which enters the distillation column. So now we are into distillation column. We know the molar flow rate remains the same before the heat exchanger. Composition will remain the same, except which we have calculated here. All right, 0.36. We know the temperature. We know the enthalpy. We realize that this feed is colder. It's not saturated, although it is preheated. So again, one has to go back to this TXY diagram and see, corresponding to 0.36, what is the temperature at which the feed will be saturated, or the bubble point temperature, etc. All right. Then it talks. Then we had the problem statement about this condenser. This condenser, if you recall from our previous discussion, condenser could be total deflux condenser or it could be partial condenser. In this problem, we were given total condenser, which means the top product after condensation is saturated, and part of it is sent back to this reflux as a reflux to the distillation column. So if you know the composition of this top product, one can again go back to this TXY diagram to calculate the temperature of this top product. One can also go back to this HXY diagram to calculate the enthalpy of the liquid, which goes per kg or per kg mole, which goes as a product or goes into the distillation column as a reflux ratios. So all these points we have marked here. Then the question in the problem statement reads that the reflux ratio is 1.5 times this R minimum. All right. So first thing we have to do now is to calculate R min, so that we have the operating R as 1.5 times. And once we have this operating reflux ratios, we can mark this differential point del D Q dash. All right. Once we know the Q dash, we can calculate the condenser load. Knowing this Q dash, knowing this coordinate of this feed HF and XF, which we know here, we can extend these two lines to obtain QW. Once we know this QW, right, we can calculate this boiler load here, and then we can do the further calculations for the estimation of number of plates, etc. So let's try calculating or determining this minimum reflux ratios. Okay. So we have HXY diagram. Again, we start from HXY diagram. H, we have this HV and we have this HL, and just focus on this R minimum. How do we calculate? So this is XD, which is 0.92. We know this data point, we know this coordinate 38,610, and we had 3,640. We don't know this WD. Now, had we known this, then of course on the first point, this is Y1, we could have drawn this tie line leading from TXY diagram. So given Y1, we could have got X1, we would have connected this with this del D, then get another point here, get this another equilibrium tie line. So and then we would have proceeded like this. So stage 1, stage 2 is the first operating line, the second operating line, etc. Now how do we get R min? We also said in our previous lecture that to get R min, one has to monitor this locus of this R min as it goes up or down by changing this reflux ratio, which is L0 by D. So when we go down, right, this flow rate, this reflux ratios, then there is a risk of this operating line coinciding with this operating line. So the definition for R min, if you recall, is maximum reflux ratio which gives infinite number of plates. So essentially at infinite number of plates, we have operating line coinciding with tie line. All right, so look at the slope of this operating line and the slope of this. As we go down, the slope of this line will change. So if del D is here and we connect with certain point here, you can see that this line is gradually becoming parallel to this, and since this WD goes down and we have F which is fixed, XW will also change, will also move upward. Alright, so all we have to do is to find out that tie line which coincides with this operating curve. Alright, so if you do this again on this HXY diagram, we said that there is a possibility of a certain tie line. So this is, let's draw again here, we have this some arbitrarily del D point here, and we are connecting all these points which would have been become our operating curves. Now there is a possibility, and these are your tie lines. Now all we have to do is to find out that tie line which corresponds, which becomes parallel to this operating line, and we have to take the maximum of that tie line which becomes parallel to this this tie line. All right, now also if you recall in our previous lecture, we said that we can have ideal solutions or we can have non-ideal solutions. Very often when we have the ideal solutions, then the shape of this TXY diagram is concave downward. All right, if you have non-ideal solutions, what we are talking essentially of azeotropic solutions, azeotropic mixture. In that case, if you look at XY diagram, then we have different type of XY diagram. So if we have XY diagram, this is a 45-degree line. Very often we have this type of equilibrium curve, but there are certain non-ideal mixture, in which case we have curve like this, or we can have equilibrium curve like this. Now these are all non-ideal mixtures, okay, or azeotropic mixtures. In this case, if we have the ideal solutions like this, very often it happens that the tie line which goes through the feed, so suppose this is your feed compositions, the tie line which goes through the feed composition, and if you extend this, this will give you maximum R min. All right, so let us try to reconstruct this HXY diagram to obtain R min. So we have this HXY diagram, HV, we have HL, and we have this XT 0.92. We know this HL, HT or HL0, which is 3640 kilojoule per kilomole, and we have this HG1, enthalpy of the vapor leaving the top plate, as 38,610. So these 2 points we know, and we have this extended line here. We know this feed compositions here at 0.36, corresponding to which we have the enthalpy HF as 2530. All right, so we said that let's find out this tie line which is going through this feed. So if you take this tie line and extend, this will give us R. So again, it's very important that we understand that we require again TXY diagram to obtain this R. So we have TXY diagram here, or we have this Y versus X diagram. So generally TXY diagram is given to us. All right, so we have this YXY diagram, or we have this TXY diagram, which is like this here. Okay, so given X, we can calculate Y right here. So we have to find out that combination of Y and X which passes through this F. From here we get this R min. Now as you said earlier that in some cases it's possible that some other tie line which will might give us this R min. Okay, but in this case when the curve is concave downward like this, we have shown here, this tie line passes through this feed F. So we know R min. From this we can measure this segment divided by this segment will give us R min. So R min equals L0 over D equals Q prime min, so which is Q prime min here, minus HG1 over HG1 minus HL0 here. So now HG1 is known, HL0 is known, HG1 is known here, and if you measure the segment, this will turn out to be 0.685. So from this R min we can calculate, and Q min is, we can read from the graph here, which is 62,570. So Q dash, everything is known, one can calculate R min as 0.685. Then our operating is 1.5 times 0.685 to equal to 1.029. And once we know 1.029, we can go back and calculate our operating Q prime, Q dash minus HG1, which is same as before, HG1 minus HL0. All these quantities are known to us. From this we can calculate Q dash corresponding to differential point, operating differential point, to obtain 74.595 kilojoule per kilomole. Somebody can also take this ratios of R min and take 1.029 as the operating reflux ratios to mark this Q dash here. So either we take the segment in proportion to 1.029 to mark this Q dash, and we can read this, or we can calculate this enthalpy of 74,595 directly from this graph, or we can calculate from here. Each of this will give the same result. So the idea here is that either we calculate this Q dash, directly read Q dash directly from the graph, or we can take the segments, the ratios of the two segments from the reflux ratios, mark it, read it from the graph, or we do the calculations given from the ratios of the two, same as the difference of the enthalpies between Q dash, HG1 and HG1 HL0. In either case, we should get approximately the same results. Once we know this Q dash or del D, we can calculate now the condenser load or the heat at the condenser, which is calculated as Q dash as 74,595, which you have calculated or you have read from the graph. This will be equal to HD plus QC over D. HD we know for 3,640. D we have 84.4 kilomole per hour. So by putting all this number, one can calculate QC as 5990000 kilojoule per hour, or this is 1664 kilowatt. So now let's come back to this HXY diagram again. Now we have to calculate the boiler room. So for that, again, one has to reconstruct or start from the same HXY diagram. We have this HVHL. We know this point 0.92. We have marked this del D now. This is equivalent to Q dash. We had this Q dash min here, from which we calculated 1.5 times to obtain this number. Feed is here. So this is XF, and we have this feed HF. Now if we extend this del D and feed this way, this will intersect this line here at 0.0057. You should recognize that this line should be now Q double dash or equivalent to your del W. Okay, so if you read from the graph, one can obtain minus 43,400 kilojoule per kilomole. Alright, so 0 is somewhere here. We have HF 1530, this number. Now of course what we are trying to here is that we realize that Q dash, Q prime and F, they fall on the same line, so it's a straight line. Okay, then we can read from the graph. In other words, one can also make use of this enthalpy calculations. Since we know the enthalpy here, this divided by this will be same as this ratios. So from this also one can calculate Q dash. So the idea is that either we read the graph correctly for Q dash, or we calculate from the relation which we have. Similarly here Q dash or del W, either we read from the graph by extending this line here, or knowing this enthalpy, knowing the enthalpy of the different coordinates, different points, one can also calculate Q dash. So it's up to you whether you read from the graph or you read from this, or you calculate from the relations. So once we know Q dash, which is equivalent to your differential point for the bottom product or the stripping column, we can calculate boiler load QB over W. So which is 6000 minus QB over 132.4 kilomole per hour, that's a molar flow rate of W, to obtain QB as 6,540,000 kilojoule per hour, which is 1816 kilowatt. Alright, so we have this QB. Now the last part of this today's lecture is to calculate minimum number of plates corresponding to infinite reflux ratios and total number of plates. Alright, so one again has to go back to this HXY diagram. So we have this HV and this HL curve. Alright, and if you recall again from our previous discussion that the locus of del D points will move downward if you are looking for R min, and it goes up if you are looking for infinite reflux ratios. So when this locus goes up, this point moves up, we have all vertical line, right? So these are the operating lines which emanate from del D. If del D points moves upward, then these lines will become vertically upward, it will become parallel to this line here. In other words, to calculate this minimum number of plates at maximum reflux ratios, one has to start from HXY diagram. We know the last coordinate, alright, which is 0.92 given to us. So all we do from here, this is your Y1, first tie line, first stage we have the X1. So the top plate, vapor leaving and the liquid leaving, they are in equilibrium. Once we have X1, all we do, we draw the vertical line. So this is operating line because this comes from plus infinity. So we have plus infinity. I realize that if this point goes up, this del W point will also go down to minus infinity. So essentially we have all these vertical lines going upward like this, till we have reached, or at least we have crossed this XW, which is 0.00, bottom product was 0.0057. Alright, so not necessarily you would be able to reach this point exactly, you have to do the calculation, at least you reach this. But notice that the last tie line which you draw, this will correspond to your boiler B. So if you have done the graphically correctly, you should be able to show that you get 4.9 plates, which includes 4.9 stages, which includes a boiler. So essentially we have 3.9 plus 1. So 1, 2, 3, 4, and we have this 4.9, which is just greater than this 0.0057. So essentially we have 3.9 stages or 4 complete stages, theoretical stages, plus 1 boiler. So the calculation of this number of plates corresponding to R tends to infinity. Alright, so that's a very simple calculation. Start from Y1, draw the tie lines, draw the vertical lines, because you realize that this RD has gone up. We have a number of plates, minimum number of plates. So this corresponds to 4 plus 1 as minimum number of plates. And now the last point is actual number of stages corresponding to R equal to 1.5s, which we have obtained earlier. So R equal to 1.5 times R min. So there again you start from HXY diagram. So we have HV, HL. Now we know all these points here. We have marked here XT. We have this HG1 or Y1. We have HT, or this is HL0, or we have corresponding to this XD. Then this is del D corresponding to with this Q dash. We know this AF feed slightly cold with this XF as 0.36, and we extended these lines to come to this point, which is XW, and here we have 0.0057. All right. So to calculate the total number of plates at these conditions, or we can start from here Y1. We draw the equilibrium curve. First stage. So this vapor is in equilibrium with this. This is Y1, this is X1, and this is Y2. So it's plate 1. So Y1, X1, if you connect with this, this is the first operating line, giving a relation between X1 and Y1, Y2. So we have this Y2. This Y2 is, and again this plate is in equilibrium with the plate which leaves here. So we have this Y1, let's mark here, this is your X1 here. If we connect this from Y2, again we have this another equilibrium. So this stream is in equilibrium with this X2, so this is get X2. We connect with this del point here to obtain this vapor, which is Y3. Alright, so we march like this. Again, calculate this 1, 2, 3. We have this Y4. You will realize that first stage, second stage, third stage, and then we will have corresponding to this, we will have another fourth stage which will connect from here. You will get fourth stage, and after you, when you take this tie line, this will cross your feed line. So essentially, after the stage 4, we have the feed entry. So first stage, second stage, third stage, fourth stage. Every time you start from Y1 vapor is in equilibrium with X1, connect with this del D. We have Y2 in equilibrium with X2, connect with this del D. We have Y3. Then we have this X3, connect with this to obtain this another point here. So similarly, we have X4, X1, X2, X3, X4, Y1, Y2, Y4. When we reach the last Y4 and take the tie line, again reading from this XY diagram all the time, we have this Y versus X diagram. So every time you have to read this diagram to obtain this. Once you cross this, then remember you have to connect with this bottom differential point, which is corresponding to this XW. We have this del X, or we have this U double dash point. Then we have to extend this, then take another one. Now this would be your 4, 5, this would be your 6th stage. And once you have crossed this, then every time you have to connect with this. Again take this, you have the 7th stage, again connect with this. We have this 8th stage, connect with this. You will realize that after this 8th stage, the 9th stage will exceed this 0.0057. So it means we require total number of stages 8 plus 1. This one is the last stage, which is boiler. Okay, so if we recall our discussion, we have the last plate here 8, starting here with 1, and the last reboiler acts as a theoretical stage because the product and the vapor and the liquid, they are in equilibrium. So the last stage 9 drawn here represents this boiler. So we have essentially 8 plus 1 stages here. Alright, so in this lecture we have taken this example based on Ponchon-Severett methods, where we have addressed how to calculate minimum number of reflux, how to calculate total number of plates corresponding to 1.5 times R min, or we have this minimum number of plates corresponding to infinite reflux ratios. So essentially start with hxy and mark all your enthalpy points, xy coordinates, and then do this staging, trying to identify that every stage vapor and liquid, leaving the two products they are in equilibrium. All right. So based on this, we can also do some other calculations like the ratios of the molar flow rates of L1, G1, L2, G2, etc. Every time you have to realize that we are writing these differential equations. The difference between the liquid energy and the vapor reaching that plate is a constant given by this top enthalpy. Similarly, we can do the for the bottom stripping sections, that whatever liquid leaves and whatever the vapor reaches that plate, the difference is also same as your bottom product enthalpy or the species. So once we mark del D and del W, then our calculation becomes simpler. We can do the calculation for condenser load, for the heating load, how many plates are required, for the two extreme cases of minimum reflux and the maximum reflux or infinite reflux. So when we have the minimum reflux, we look for that tie line which passes through this feed compositions. We say that typically it happens that most of the ideal solutions that they have XY diagram concave downward. But in some cases when we have acid troughs, then we have to be extra careful. We have to find that it's possible that some tie line can give maximum number of maximum reflux, which is larger than corresponding to the tie line which passes through this feed composition. So that happens only in case of non-acid or acidotropic mixture or the non-ideal mixture. So, and once we have this R min, we can calculate operating R, which is typically 1.5 times the minimum reflux ratios. Similarly, if we are asked to calculate the minimum number of plates corresponding to infinite reflux ratios, in that case the points goes upward, both del D and del W goes downward. We have all the operating lines vertically. In that case, all we are supposed to do is starting with y1, calculate x1, draw a vertical line, get y2, draw this x2, draw the vertical lines, and find out how many minimum number of plates are required for this maximum reflux ratios. So that's the example on Ponchon-Severett methods. We have taken two examples. You are encouraged to solve as many as problems from both Treball as well as B.K. Datta's book, separation processes. The next time we meet, or the next lecture, we will take up a new topic on distillation column, but by different methods called Machiavelli method. Okay, thank you.